Hey guys, so the last lesson we talked about different types of bonds and we differentiated between organic and inorganic chemistry. So let's just recap. Organic compounds have carbon covalent bonds and typically involve carbon and then a hydrogen and or oxygen molecule. They're not water soluble and typically make up larger molecules, for example sugars. Inorganic compounds will have electrolytes, they have stronger ionic bonds, but they also dissociate or dissolve in water. So the most important inorganic compound in the body would have to be H2O, or water. It's a solvent, which means that it's a liquid, and other things can dissolve in it, called solutes. This is how we get sodium and chloride ions into our cells so they can be used, instead of having clumps of table salt just floating around in our veins. Besides helping inorganic compounds dissolve, it also helps facilitate organic compounds growing or shrinking. If you want to have smaller molecules stick together, pull some water out. It's called dehydration synthesis. To break a large organic molecule into two smaller ones, add some water, and this is called hydrolysis. So why would we want to do this? Well, there's loads of reasons. The most common reason has to do with energy. ATP is adenosine triphosphate, and this is the energy or fuel that our body runs on. And we generate ATP from breaking down sugars, which we get by breaking apart or hydrolyzing really large carbohydrate molecules. So like I said before, water is key to inorganic chemistry. It helps ionic bonds dissolve and separate. It acts as a medium for these reactions to happen. It's these dissolving of these bonds that leads us to our next topic, acidity. So if we took a glass of water and looked down at it at the chemical level, inside the water, which is H2O, you'd see an equal number of hydrogen and hydroxide floating around. If they were on a scale, the hydrogen on one side and the hydroxide on the other, they'd be completely balanced. That scale is called the pH scale. And to put some numbers on it, pure water, it was right in that middle, would have a pH of 7.0. Acids are liquids that have excess hydrogen ions floating around in them. So for example, if we added hydrogen chloride to water, the hydrogen separates from that hydrogen chloride, tips the scales more out of balance. The more hydrogen ions we add, the more that scale tips out of balance and the more acidic our compound becomes. Acids are defined as anything that has a pH of less than 7. The opposite of an acid is called a base. So this is a liquid that instead of having free hydrogen ions, it has free hydroxide ions, which are OH minus. So following our example, if we added baking powder, which is sodium bicarb, it would split up into a lot of hydroxide ions, and that would tip the scale towards our other solution. The more bicarb, the stronger the base, and the higher the pH. Any pH higher than 7.0 is considered basic or alkaline. So that's a lot of chemistry, but again, why do I care? Well, we need certain concentrations of sodium, potassium, and calcium in our bodies for our nerves and muscles to function. If we don't have enough, then our brains don't operate and our heart can't beat. We need hydrolysis and dehydration reactions to break down sugar and ATP to give our cells the energy it needs, and all of these reactions only work if our body's pH is kept at a certain range, between 7.35 and 7.45. That's not a lot of wiggle room, but we have what's called buffers, which help keep us there. It's a really small thing, but letting that pH get out of range too far for too long can have huge consequences.